Okay, so Fast TVB is basically a fast implementation of the reduced Wang-Wang neural mass model in C and deployed as a Docker image, so it can be run in a container. So no dependencies need to be installed, and also the compiler and stuff is all done through Docker containers. So this is also platform independent. What services from the eBrains cloud is the software using? It uses Lab with its Jupyter Notebook as a front end. Then Drive again to upload data and input data and to download results and to transfer data back and forth between supercomputer and eBrains, and Wiki for documentation. So the key feature of this software is that it is a re-implementation of the simulator core of TVB, which is faster than the Python implementation because it is implemented in the hardware language C and makes use of a number of optimization techniques that decrease the waiting time for the CPU basically and optimize the whole simulation workflow. And it's also parallelized, which means that you can spawn multiple threads and basically compute a brain network model over several CPUs. The code is basically just a single C file. So in order to optimize this code, it's basically follows the opposite direction of many good software engineering practices, meaning it's not modular. It's basically opposite. Everything is very streamlined, the flow is very sequential, so that there are not much context changes and so on, which all cost valuable CPU cycles. So it's a very highly optimized workflow, which is hard to read, but this is also not the goal here. It's open source. There is a GitHub repository which explains how you can generate a Docker container from here, so you don't need to know C or how to compile C code. So it's basically automatized from this perspective. And there's the execution-ready image hosted on Docker Hub, which can be pulled and used on any machine that is able to run container images. And as a front end also that shows the operation from or within the eBrains cloud. There is a Jupyter Notebook at eBrains, also implemented or stored inside a Colab, a dedicated Colab, where there's a drive with accompanying examples and the wiki with documentation. What are the data formats? So this Fast TVB uses a very simple format, storing all inputs and outputs as plain text ASCII files. So all we need are basically two folders, input and output. And within these folders, we can store our weights and distances matrices again. And we also have a parameter set configuration. So weights and distances, similar to the input format for TVB, is basically just a CS3 file or a TS3 file with floating point numbers. And the parameter set likewise is just a sequence, a list of numbers. This is not optimal. This is clearly one point where this can be improved, namely that parameters are specified as key value pairs in a JSON format, for example, to make it more readable and fault tolerant. The outputs are then in this version region-wise fMRI time series. So this is also just an plain text ASCII file that contains just a sequence of floating point numbers, basically. So an n times t matrix where we have regions times time points basically as output. The parameters are the parameters of the reduced Wang-Wang model. So we have a global coupling scaling factor, which is very often needed to tune a brain network model, which retunes, which rescales the strengths of global interaction, of large scale interaction, basically which rescales the structural connectome to optimize the fit with functional connectivity, basically. The API is very simple. It's command line arguments, basically. There are 3 command line arguments, basically. You invoke the Docker container, basically, and mount bind the paths where the output and where the input shall be stored. And all that you need to specify then is the parameter file, the subject ID, and the number of threads that should be spawned for this process. So basically, in order to run large parameter scale explorations, you can create any number of parameter files and then can run basically any number of instances of this process, basically as many as your computer has CPUs, and thereby fully employ all CPUs. Or if you want faster execution, you can also increase the number of threads per instance, which then allows you to not explore as many parameter sets in parallel as you have CPU cores, but which makes the execution faster. The software, some words about software maturity, integration, testing, versioning, and deployment. So maturity, the software was used in around 8 publications right now, but there are many ways in which this could be improved. So that parameters could, for example, be specified as key value pairs. We could allow more input-output formats, especially output formats. So at the moment, we're just writing out FMI, but this can be easily adapted to other signals that are simulated within this model. We could use the same approach to implement different neural mass models, and also clean up the code and revisit these optimization techniques. So this is quite some time ago when this was initially conceptualized, and with compiler updates and new architectures, several things might be updated. It was tested intensively by 5 different persons. So this was me and 4 authors of papers, basically, which used this code, at least that I'm aware of. Then versioning is achieved by giving the Docker images and the source codes version numbers at Docker Hub and GitHub, and letting these older versions also remain as legacy versions in these repositories. And that's the end already.